Tonight, we will quietly explore a question that has puzzled and haunted humanity ever since we first looked up at the twinkling stars in the night sky. It's a question that sounds deceptively simple, but the answer is profoundly grim. Why haven't we yet traveled beyond our own solar system? The problem isn't that our technology isn't advanced enough, nor is it due to limited funding for science. The problem lies in something much deeper, far more permanent and unchangeable. The fundamental laws of the universe seem to have quietly built an invisible prison around us, a solid barrier that no amount of human ingenuity or intellect can break through. By the end of this journey, you will understand exactly why we are confined to this tiny corner of the cosmos, and why, perhaps, we will be forever. Before we begin, if you enjoy detailed, historical content like this, a like or a subscription would greatly help the channel's growth. It's just a small gesture, but it makes a huge difference for this project. And now, please, relax your mind as we begin our journey. Let's start with something you may have heard of, but whose immense and terrifying scale we rarely truly comprehend. The star closest to our Sun is named Proxima Centauri. It's a small, faint red dwarf star located about 4.24 light-years away from us. When we talk about a light year, we are referring to the distance that light can travel in one full year at the incredible speed of 300,000 kilometers per second. This means that for every light year, light travels a distance of about 9.46 trillion kilometers. Since Proxima Centauri is 4.24 of these units away, the actual distance is about 40 trillion kilometers. Try to repeat that number in your head. 40 trillion kilometers. This is a number so vast that the limited human mind simply cannot process or fully visualize it. To help you get a better picture, let's look at reality. The fastest space probe ever built by human hands is the Parker Solar Probe, a device specifically designed to study our star. At its maximum speed, this probe reaches about 700,000 kilometers per hour as it approaches the Sun. That is an astonishing velocity, faster than anything we have ever created in history. Yet, even at that extraordinary speed, the probe would still take more than 6,500 years just to reach Proxima Centauri. Take a moment to reflect on that. 6,500 years. By the time that probe finally reached its destination, more time would have passed on our blue planet than the entire period since the first pyramids of Egypt were built. The entire recorded history of human civilization, from ancient Sumer to the present day, would fit within the duration of that journey, and there would still be thousands of years left to go. And remember, that's just the journey to the nearest star. The Milky Way, our beloved home galaxy, has a massive diameter of about 100,000 light-years, containing anywhere from 100 billion to 400 billion different stars. If we wanted to cross the galaxy from one end to the other at the speed of the Parker Solar Probe, it would take us about 150 million years. Let's recall a bit of geological history. The dinosaurs went extinct about 66 million years ago. This means that if you had started that journey across the galaxy when dinosaurs still ruled the Earth, you would have traveled through their entire era, witnessed their extinction, then seen the rise of mammals, the evolution of primates, until humans appeared and created all of recorded history. And even after all that had passed, you would still only be about halfway to your destination. We are no longer talking about mere distances that are beyond our current technology. We are talking about distances that are beyond any biological timescale, any geological timescale, and even beyond the time it takes for species to evolve. But you might think this is just a matter of speed. If we could build faster ships, if we could get closer to the speed of light, then perhaps we could do it. After all, light only takes 4.24 years to travel from Proxima Centauri to here. If we could travel at 10% the speed of light, we would arrive in 42 years. That's a lifetime, yes, but at least it's within the realm of possibility. a young person could leave Earth and reach Proxima Centauri as an old person. It would be incredibly difficult, but it doesn't seem impossible. However, this is where reality begins to reveal its most brutal limits. Reaching 10%, the speed of light, which is about 30,000 kilometers per second, isn't just a difficult challenge with today's technology. Theoretically, it might be impossible for any crewed vessel, no matter how advanced our technology becomes. Let's talk a little about energy. The amount of energy required to accelerate an object increases exponentially as you approach the speed of light. This isn't a limitation of machinery or engineering. It's a fundamental law of physics described by Einstein's theory of special relativity. As an object moves faster, its effective mass increases. The faster it goes, the more energy you need just to accelerate it a little bit more. At speeds approaching the speed of light, the required energy becomes absurdly large. Let's do a few rough calculations to get a clearer picture. Suppose we want to send a 1,000-ton spacecraft, roughly the mass of the International Space Station, at 10% the speed of light. The kinetic energy required to do that would be about 4.5 times 10 to the power of 21 joules. To put that into perspective, that enormous number is equivalent to the total energy consumption of all of human civilization for several years straight. It includes all the electricity generated by every power plant on the planet, every drop of fuel burned, every solar panel and wind turbine operating continuously for years, all just to provide enough acceleration energy for a single ship to reach 10% for the speed of light. And that's just the energy for acceleration. You would also need to decelerate as you approach your destination, which would require an equivalent amount of energy once again. So, in reality, you're looking at twice that staggering number. Furthermore, this is assuming perfect efficiency, meaning every single unit of energy you generate is used directly to propel the ship with no loss whatsoever. In the real world, no system can achieve such perfect efficiency. Current conventional rocket engines have an efficiency of only a few percent. Even the most efficient theoretical systems we can imagine could only achieve a maximum efficiency of 50 to 70%. This means the actual amount of energy you would need to generate would be many times greater than what we just calculated. So, where would we get all this tremendous amount of energy? Traditional chemical rockets are certainly not going to work. Chemical fuel simply does not contain enough energy per unit of mass to meet this requirement. If you tried to use chemical rockets to achieve even a significant fraction of the speed of light, the mass of the fuel you'd need to carry would become an astronomical figure. In fact, you can calculate that no matter how much fuel you try to pack, you could never carry enough to reach that velocity. The required fuel mass increases exponentially with the desired speed, and you quickly reach a point where you would need more fuel than the mass of our entire planet combined. Chemical rockets have taken humans to the moon. They have allowed us to send probes across the solar system, but they are completely inadequate for long-distance interstellar journeys. What about nuclear propulsion then? The process of nuclear fission can release about 1 million times more energy per unit of mass than conventional chemical reactions. A fission reactor would work by splitting heavy atoms like uranium or plutonium, thereby releasing a large amount of energy in the process. Various types of nuclear fission engines were proposed by scientists decades ago. The most notable was Project Orion, conceived in the 1950s and 60s, which proposed using successive nuclear explosions to propel a spacecraft. Essentially, you would detonate nuclear bombs right behind the ship, and the shock waves from the explosions would push the ship forward. It sounds incredibly dangerous and impractical, and it was, but mathematically, it could work. Initial estimates suggested that a Project Orion engine could help a ship reach up to 5% the speed of light, or maybe even 10% with the most optimistic designs. While that's much better than chemical rockets, you'd still be facing journeys of 40 to 80 years just to get to Proxima Centauri. And remember, that's just the closest star to us. Project Orion never materialized, partly due to international treaties banning nuclear weapons in space, but mostly because of the enormous technical challenges. To make it work, you would need thousands of nuclear devices, and each one would have to be detonated in perfect, absolute synchrony. Besides that, you'd also need a shock-absorbing shield strong enough to withstand the continuous, repeated nuclear blasts. And most importantly, you'd have to protect the crew from the deadly radiation. In principle, these problems are not entirely unsolvable, but they are truly monumental challenges. Even if you could overcome all these hurdles, you'd still be limited by the amount of fissionable material you could carry on board. Nuclear fission has a fundamental limit on how much energy it can produce per unit of mass. So, what other options do we have? Is nuclear fusion the answer? This is the very process that powers the shining stars, and it can provide an even greater amount of energy. Fusion works by combining light atoms, usually hydrogen, to form heavier atoms like helium, thereby releasing an enormous amount of energy. In the scientific community, nuclear fusion has always been considered the holy grail of energy production on Earth. We have been persistently trying to build practical fusion reactors for decades. Although humanity has made noteworthy progress, to this day, we still don't have a single operational fusion power plant that can generate more energy than it consumes. However, let's set aside the current difficulties for a moment and assume that one day we solve this fusion problem. Let's imagine we can build a highly efficient fusion engine specifically for a spacecraft. The question is, how far would that get us? Scientific calculations suggest that, in theory, a fusion engine could accelerate a ship to 10% or maybe even 20% the speed of light. If that were achieved, the travel time to Proxima Centauri would be shortened to about 20 or 30 years. This is still a lifetime, but it starts to seem more feasible. You could send a crew of young people, and they would reach their destination in their middle or old age. However, the difficult problem is that building a fusion engine for a spacecraft is vastly more difficult than building a stationary reactor for power plants on the ground. Here on Earth, you can build massive, heavy reactors with enormous magnetic fields to contain and control the plasma. But in deep space, every single kilogram of mass is critical. You would need an engine that is both lightweight and compact, and it must be capable of producing sustained thrust for many years or decades without any failures. On top of that, you'd need a special fusion fuel, perhaps deuterium and helium-3, which are inherently rare and extremely difficult to find in large quantities. Furthermore, you'd have to deal with the immense amount of heat radiated by the fusion reactions. You can't just simply let that heat radiate into the vacuum of space as easily as we might think. A vacuum is actually an excellent insulator. Therefore, the radiators needed to dissipate the heat from a fusion engine would have to be extremely large and incredibly heavy. Even if we could overcome all those technical hurdles, we would still face another fundamental problem: the fuel itself. A fusion engine must always carry its own fuel. Unlike an airplane that can stop to refuel, an interstellar ship has absolutely no pit stops along its multi-trillion-mile journey. You are forced to carry all the necessary fuel right from the start, and paradoxically, the more fuel you carry, the heavier your ship becomes, which means you need even more fuel just to accelerate the mass of the fuel itself. This problem is widely known as the Tsiolkovsky rocket equation. It sets a fundamental limit on the velocity you can achieve based on the amount of fuel you can carry. To reach a truly high velocity, a very large fraction of the ship's mass must be dedicated to fuel. At speeds approaching relativistic velocities, the vast majority of your ship's mass would be nothing but fuel, leaving very little room for cargo, the crew, life support systems, and other essential equipment. To solve this bottleneck, there was once a proposal that sounded very clever. What if we didn't need to carry the fuel from the beginning? What if we collected it along the way? This bold idea is called the Bussard ramjet, proposed by physicist Robert Bussard in 1960. The main idea is to use an enormous magnetic field to scoop up hydrogen gas from the interstellar medium, the thin gas that exists in the space between stars. Then, you would use that very hydrogen as fuel for a fusion engine. In theory, as long as there is hydrogen in space, your ship could continue to accelerate indefinitely. You would never run out of fuel because you are constantly collecting it as you move. Sounds perfect, doesn't it? But reality is much harsher. Interstellar space is actually extremely empty. The average density of the interstellar medium is only about 1 hydrogen atom per cubic centimeter. That density is 1,000 billion times lower than the best vacuum we can create in a laboratory on Earth. To collect enough hydrogen to power a fusion engine, you would need a magnetic collector of an enormous size, perhaps thousands of kilometers in diameter. The mass of the magnets and the equipment needed to generate such a huge magnetic field would be staggering. Moreover, as you accelerate faster, the drag caused by collecting that hydrogen could slow you down more than the thrust the engine generates to push you forward. Scientific calculations have shown that the Bussard ramjet might not work at all in the actual density conditions of the interstellar medium. In theory, it's a beautiful concept, but in practice, it seems unfeasible. So, nuclear fusion, even in the best-case scenario, could only get us to speeds of 10 to 20% the speed of light. And that's still assuming we've solved a host of huge technical challenges that we currently cannot overcome. So what about going even faster? How do we get closer to the speed of light? This is where the laws of physics become truly merciless. Antimatter is the most energy-dense substance we know of. When matter and antimatter meet, they undergo total annihilation, converting 100% of their mass into pure energy. This follows Einstein's famous equation, E equals mc squared. No other natural or artificial process we know of offers such incredible energy efficiency. If we could use antimatter as fuel, we could theoretically accelerate a spaceship to speeds very close to the speed of light, perhaps 90% or even higher. However, the biggest problem is that antimatter doesn't exist naturally in usable quantities. We are forced to create it in massive particle accelerators, and this production process is extremely expensive and arduous. CERN, the European Organization for Nuclear Research, which is the world's largest particle physics laboratory, can currently only produce a few nanograms of antimatter per year. You know, a nanogram is just 1/1,000,000th of a gram. To provide enough energy for a spaceship, you would need kilograms or even tons of antimatter. At the current rate of production, it would take us billions of years just to accumulate that much fuel. Even if we could somehow miraculously mass-produce antimatter, storing it would be an absolutely immense challenge. Antimatter is immediately annihilated the moment it touches any kind of regular matter. Therefore, you would need to store it in special magnetic or electric field traps to prevent it from touching the container walls. These traps require constant energy to operate, and any minor failure would lead to a catastrophically powerful explosion. Then there's the problem of how to use antimatter for propulsion. When matter and antimatter annihilate each other, they primarily create gamma rays, which are extremely high-energy particles of light. Gamma rays are very difficult to direct or use to generate thrust in a specific direction. Most of the energy would simply radiate out in all directions, instead of pushing your ship forward. Converting antimatter annihilation into useful thrust is another great engineering challenge. Thus, even with antimatter, our speed would likely be limited to about 50 to 90% of the speed of light at most. Now, imagine when we reach speeds really close to the speed of light, say 90% or more. At this point, the effects of special relativity become incredibly important. Time would dilate for the people making the journey. If you were traveling at 90% of the speed of light, time would pass significantly slower for you than for those who remained on Earth. A trip that lasts 10 years, according to clocks on Earth, might feel like only 4 or 5 years have passed for you. This is a physical reality, not something out of science fiction movies. Clocks on ships flying at high velocities really do run slower. At even higher speeds, let's say 99.9% of the speed of light, time dilation becomes unbelievably extreme. You could travel for decades or even centuries, according to Earth's clocks, but to you, the trip might only last a few short years. This might sound like good news, as it makes long interstellar journeys more bearable for the crew. You could travel to distant stars without aging very much. However, there's an incredibly painful catch hidden within this. While you only experience a few years on the ship, all your loved ones on Earth continue to age at a normal pace. You return home from a trip that you thought was only 5 years long, but in reality, 50 or even 100 years have passed on your home planet. All the people you once loved and knew are gone. Society has changed so much that you can't recognize anything. You have effectively become a time traveler thrown into the future with no way of returning to the past. This raises a profound philosophical question. Is this truly a round trip? Physically, the answer is yes. You can return to the same planet, but in every spiritual and social sense, the Earth you return to is a completely different place. You can't reunite with your friends or family. You can't share your precious experiences with the people who tearfully saw you off. You are alone, like a stranger from your own future. This turns interstellar travel into a permanent exile. Once you decide to leave, you can never truly come home again. This isn't a technical limitation, but a fundamental and inevitable consequence of how space-time works. Even if we had the most perfect technology in our hands, this grim reality would always exist. Imagine just a single hydrogen atom colliding with your ship at 90% of the speed of light would carry an enormous amount of energy, roughly equivalent to a bullet just fired from a rifle. Now, try to picture your ship being hit by billions of such bullets every single second. With this terrifying density of impacts, your ship's hull would be rapidly eroded and severely damaged. Even worse, these high-speed collisions would create a phenomenon called secondary radiation, producing a shower of high-energy particles right inside the ship's cabin. This stream of radiation would be lethal to any crew members, even if the ship were equipped with thick shielding. Protecting humans from this type of radiation is an extremely difficult problem. Some scientists have proposed using a magnetic shield, similar to how Earth's magnetic field protects us from the solar wind, to deflect charged particles. However, interstellar space contains not only charged particles, but is also filled with neutral particles, which are completely unaffected and undeflected by magnetic fields. Furthermore, at truly high velocities, even particles of light carry enough energy to become a threat. The light from the stars you are flying towards will be blue-shifted, causing them to shift to higher energy wavelengths. Due to your incredible speed, visible light would transform into harmful ultraviolet rays or even X-rays. At that point, you would be moving through an intense radiation storm created by your own velocity, and it doesn't stop there. We also have to contend with larger dust particles, microparticles that occasionally drift through interstellar space. A single particle, the size of a tiny grain of sand, hitting your ship at 90% of the speed of light would create a devastating impact equivalent to a small nuclear bomb. Such a collision could tear apart and destroy your ship instantly. Detecting and avoiding these dust particles is nearly impossible. You would be moving so fast that you couldn't possibly react in time. The moment you realized there was a dust particle in your path, your ship would have already slammed into it. Therefore, you would need a special kind of shield in front of the ship, something that could be sacrificed to absorb all impacts in order to protect the rest of the vessel. But this shield would have to be incredibly large and would need to be constantly replaced or repaired throughout the journey. Some designs have proposed multi-layered shields, basically a form of spaced armor that helps vaporize incoming particles before they can reach the main hull. However, this adds significant mass to the ship, which in turn demands even more energy to accelerate. The faster you try to go, the worse the problems of radiation and cosmic dust become. This is another fundamental limit, a reminder that the universe doesn't seem to be designed for living beings to traverse it at relativistic speeds. Now, let's talk about something that seems like a solution for long journeys: a generation ship. If the journey is too long for a single lifetime, why don't we send a ship large enough to sustain an entire community of people for multiple generations? The first generation would leave their beloved Earth, live their entire lives on the ship, have children, and eventually pass away. Their children would grow up on that ship, never knowing the ground or sky of Earth, and they too would go on to have the next generation. This process would continue for decades or even centuries, until the ship finally reached its distant destination. The last generation would be the ones to explore the new world, completing the great mission their ancestors began so long ago. The concept of a generation ship has been a familiar element in science fiction stories for decades, and in principle, no law of physics forbids us from doing it. They don't require strange physics or impossible energy sources. They only require a truly massive ship with a self-sustaining life support system and a population willing to dedicate their entire lives to the journey. However, when we delve into the details, the challenges begin to seem overwhelming. First, let's talk about size. To sustain a healthy human population for generations, you would need an incredibly vast space. We humans are not good at living in cramped, confined environments for long periods. Studies on long-term isolation, such as simulated missions to Mars, have shown that even small groups of highly trained professionals struggle with severe psychological effects from confinement after just a few months or years. Now, try to imagine entire generations of people being born, growing up, and growing old in the same single, enclosed environment. They would never experience the feeling of standing under an open sky, never see the vast ocean, dense forests, or majestic mountains. These are the very things that we humans have evolved over millions of years to find comforting and inspiring. To avoid serious psychological problems for the crew, you would need to create a living environment that feels spacious and diverse. This means your ship would have to be enormous, perhaps several kilometers in diameter, including multiple residential areas, green spaces, and even artificial lakes. But the larger the ship, the heavier its mass, which brings us back to the same problem. You need even more energy to accelerate it. The mass would increase astronomically. A generation ship could weigh millions of tons, or even more. Accelerating such a massive object to 10% the speed of light would require an amount of energy far beyond anything our current civilization can produce. Even if we were to use nuclear fusion or antimatter, then there is the critical issue of life support. Humans always need air to breathe, water to drink, food to sustain them, and an effective waste management system. On short journeys, we can bring supplies or use simple recycling methods. But on journeys that span generations, you must have a closed-loop system that is almost absolutely perfect. Every single atom of carbon, nitrogen, hydrogen, and oxygen must be recycled over and over again for decades without any significant loss. We know from practical experience on the International Space Station and other space missions that current life support systems are still far from perfect. There are always leaks, inefficiencies, and the buildup of contaminants. Over time, these minor issues would become extremely serious. On a mission lasting centuries, even the slightest inefficiency could lead to the depletion of your precious resources. Therefore, you would need self-sustaining ecosystems, essentially a miniature Earth placed inside the ship, with plants to produce oxygen and food, bacteria to break down waste, and a complete water recycling system. We have tried to create such closed ecosystems on the ground, most notably the Biosphere 2 project, but the results were not entirely successful. Maintaining a stable ecological balance over a long period is an incredibly difficult challenge. Any imbalance, whether it's the extinction of one species or the overgrowth of another, could cause the entire system to collapse. On a lone starship, you can't simply open a window for fresh air or import more food if your crops fail. You are entirely on your own in the void. Furthermore, we must also face the problem of maintenance and repair. Over hundreds of years, mechanical systems will inevitably wear down, parts will fail, computers will need upgrading, and the hull might develop microleaks. On Earth, we can easily manufacture spare parts, import raw materials, or call in specialists. But on a generation ship, you have to be completely self-sufficient in everything. You need to carry all the spare parts or be able to manufacture them on the spot. This requires workshops, raw materials, and complex tools, all of which add even more mass to the ship. And you also need people with the skills to use these tools, from engineers and technicians to scientists. But how do you maintain and pass down this vast body of knowledge over many generations? What would happen if a critical area of expertise was lost simply because no one in a particular generation chose to study it? Or what if crucial stored information became corrupted and no one remembered how to repair an essential system? Next is the difficult problem of social governance. How can you manage a completely isolated human population for multiple generations? What happens if political or social conflicts arise? On Earth, dissatisfied people can choose to move elsewhere, form new communities, or rebel. But on a starship, everyone is trapped with nowhere to go. Any conflict could escalate into violence and threaten the safety of the entire mission. You would need extremely stable social structures that could endure for centuries to maintain morale, a sense of purpose, and cooperation among people. This is something no human society on Earth has ever achieved for such long periods without experiencing profound upheaval or change. Finally, we cannot ignore the issues of motivation and genetics. The first-generation volunteers because they understand and believe in the grand objective. But what about the generations born later? They grow up on the ship without a choice. To them, the destination planet might be as vague as a fairy tale. Why should they dedicate their entire lives to completing a mission started by people who died long before they were born? What happens if they decide they no longer want to continue the journey? In addition, a small population living on the ship would face the risk of inbreeding. Over time, this would lead to serious genetic problems. You would need a founding population large enough to maintain genetic diversity, perhaps several hundred or even thousands of people. But the more people you have, the larger the ship must be, the more resources it needs, and of course, the more enormous the amount of energy required to accelerate it. An ideal generation ship would essentially have to be a small, completely self-sufficient world. It would be a colossal vessel capable of sustaining an entire civilization for an indefinite period. However, building such a magnificent structure would require resources and a level of technology far beyond our current human capabilities. And even if you could build it, you would still have to face enormous risks. A single point of failure could lead to a horrifying disaster. A system malfunction, a radiation leak, or a sudden epidemic could wipe out the entire population of the ship. At that point, there would be no rescue team and no help from the outside. You would be utterly alone, surrounded only by the vast darkness between the distant stars. Faced with these mounting difficulties, some scientists have proposed another solution: deep, cryopreservation. Instead of trying to keep the crew alive and functioning normally for centuries, why don't we just freeze them? You would temporarily suspend their biological functions, placing them in a state of deep hibernation, and only wake them up when the ship reaches its destination. This way, we wouldn't need enormous generation ships or complex self-sustaining ecosystems. You would only need to keep the bodies frozen and ensure the ship's most critical systems remain operational. The crew would experience the long journey as nothing more than the blink of an eye. They would fall asleep on Earth and wake up in a completely new star system. Sounds perfect and peaceful, doesn't it? However, the biggest problem is that cryopreservation technology doesn't actually work yet, at least not in the way we need for interstellar travel. Currently, we can only freeze cells, small tissues, or even some organs, and revive them with varying degrees of success. But freezing an entire human body and then reviving it without causing any damage is something humanity has never achieved. The main obstacle lies in the formation of ice crystals. When you freeze biological tissue, the water inside the cells crystallizes into ice. These crystals are incredibly sharp and hard. They will puncture the cell membranes, completely destroying the delicate structures within. By the time you try to thaw the body, all you'll have is a complete mess. The cells would be ruptured, their membranes riddled with holes, the organelles severely damaged, and the entire body's tissue would essentially turn into a lifeless mush. To overcome this, there are techniques called vitrification. Instead of conventional freezing, scientists try to put tissues into a glass-like state by using cryoprotectants. These are special chemicals that prevent water from crystallizing. This method works better than simple freezing, but it brings its own set of problems. Cryoprotectants are often highly toxic in large concentrations. You need to circulate these chemicals throughout the entire body to replace blood and tissue fluid. Then, you need to cool the body very quickly and uniformly, which is extremely difficult to do with an object as large as a human. Different parts of the body will cool at different rates, leading to thermal stress and causing cracks to form in the tissue. Even if you succeed in vitrifying a body, storing it for decades or centuries presents immense challenges. You need to maintain an extremely low temperature, typically using liquid nitrogen at -196 degrees Celsius. Any temperature fluctuation, or even the slightest warming, could trigger crystallization or cause tissue fractures. And then there's the arduous process of reanimation. You have to thaw the body uniformly and quickly, completely remove the toxic cryoprotectants without damaging the tissue, restart the heart, breathing, and somehow miraculously restore brain function without losing the person's memory or personality. Currently, all of this is completely beyond our capabilities. Some companies today offer cryopreservation services for the deceased by freezing their bodies or just their brains, with the hope that technology in the distant future can revive them. But we need to be frank. This is currently based more on faith than on proven science. No one has ever successfully revived a mammal after deep cryopreservation, let alone a human. Even assuming that future technology could solve all these problems, other complexities remain. On a centuries-long journey, the ship's systems would need to function absolutely perfectly. Just one small failure in the cooling system, and the crew would thaw prematurely and decompose immediately. You'd need energy sources that could last for hundreds of years, monitoring systems that could never fail, and perhaps a highly advanced artificial intelligence or computer to manage the ship and respond to emergencies without human intervention. This leads us to another tricky question. If we already have artificial intelligence advanced enough to manage an interstellar ship for centuries, why would we risk sending humans at all? This question leads to a more practical proposal: using robotic probes. Instead of sending fragile biological bodies, let's send machines. Machines don't need air to breathe, food, water, or warmth. They can withstand levels of radiation that would kill a human instantly. They can be designed to last for centuries with minimal maintenance. And if they happen to be damaged or destroyed, it's only a scientific and financial loss, not a tragic loss of human life. In fact, robotic probes are our best option for interstellar exploration in the near future. We have already sent these messengers beyond the boundaries of our solar system. The Voyager spacecraft, launched in 1977, are now drifting through interstellar space, more than 20 billion kilometers away from us. After nearly 50 years, they are still diligently transmitting data back to Earth. This is a brilliant testament to what human engineering can achieve. However, the Voyager probes move quite slowly on a cosmic scale, at only about 60,000 kilometers per hour. At that speed, it would take them more than 70,000 years just to reach the Proxima Centauri system. To explore other stars within a reasonable time frame, we must have much faster probes. A project called Breakthrough Starshot is a proposal trying to do exactly that. The idea is to build tiny probes, each weighing only a few grams, and accelerate them using extremely powerful ground-based laser beams. You would attach a thin, reflective light sail to each probe, and then shine a massive laser array on it. The pressure from the laser light would push the sail, accelerating the probe to unimaginable speeds. Calculations show that you could accelerate these tiny ships to 20% of the speed of light, fast enough for them to reach Proxima Centauri in about 20 years. This is truly a revolutionary breakthrough. You could send a probe today and, within your lifetime, have the chance to receive data and images from another star system. You could see exoplanets up close, study their atmospheres, and search for signs of life, all without sending anyone into harm's way. However, Breakthrough Starshot also has its own enormous challenges. First, you need to build a laser array capable of generating gigawatts of power, focused with absolute precision, on a tiny sail moving at incredible speed. This requires huge advances in laser technology and energy production systems. Then, the probes themselves must be extremely light, just a few grams, yet still integrate cameras, sensors, computers, and transmitters. They need to survive the intense acceleration and endure a 20-year journey fraught with dust and radiation. And finally, there's the problem of communication across vast distances. At a distance of 20 light-years, a radio signal will take exactly 20 years to return to Earth. This means that from the moment of launch, you have to wait 20 years for the ship to arrive, and then another 20 years for the data to come back. That's a 40-year commitment just to get the first results. Despite the difficulties, robotic probes are entirely feasible because they don't violate any laws of physics. If humanity focuses enough resources, we could achieve this in the next few decades. But remember, this is a journey of exploration, not colonization. These machines cannot build homes, they cannot bring samples back, and they cannot be a backup home for humanity. To achieve even greater things, we need cosmic shortcuts. Now, let's talk about something that sounds like it's from the movies, but has a real basis in physics: wormholes and warp drives. A wormhole is a shortcut through the fabric of space-time, like a tunnel connecting two distant points in the universe. In theory, if you could find or create a wormhole, you could enter one end near Earth and step out the other end near Proxima Centauri almost instantly. You're not moving faster than light, you're simply taking a shorter path. This amazing idea comes from Einstein's theory of general relativity, which describes how gravity can bend space-time. However, the truth is that wormholes, if they exist at all, would likely be extremely fragile and unstable. They would collapse instantly the moment you tried to step inside and use them. To keep a wormhole open, you would need something very special called exotic matter, with negative energy density. Please note, this is not the antimatter we've discussed before. It's something much stranger and more mysterious. This type of matter possesses a property called repulsive gravity, pushing things away instead of pulling them in as usual. To this day, humanity has no practical evidence that this exotic matter exists in large enough quantities to be useful, if it even exists in the universe at all. Some physicists believe that the Casimir effect, a fascinating phenomenon in quantum physics, can create negative energy density, but only on an extremely tiny scale. However, harnessing this phenomenon on a macroscopic scale, large enough to create a wormhole a person could travel through, is completely beyond our current technology, and perhaps even beyond what the laws of physics allow. Even if you could create a wormhole, it would still need to be stabilized and positioned with absolute precision, with one end near Earth and the other near your destination. But how would you move one end of the wormhole to its destination? You would still have to get it there using conventional, slower-than-light methods, which brings us right back to our original problem. Therefore, while wormholes may sound appealing in theory, in reality, they are far too remote to be a viable solution. They seem no different from a type of magic from mythology. We cannot build them. We don't know if they truly exist, and we have absolutely no way to stabilize or control them, even if we could create them. Next, let's talk about the warp drive. This idea was widely popularized by the Star Trek films, but it's actually based on a real physics concept proposed by physicist Miguel Alcubierre in 1994. The principle of the warp drive is to distort the fabric of space-time around your ship. It would contract space in front of the ship and expand space behind it. The ship itself would rest peacefully within a bubble of flat space-time and wouldn't move through space in the conventional way. Instead, space itself would move around you, because space can expand or contract faster than the speed of light. In theory, there is no speed limit to this. You could travel faster than light without violating Einstein's theory of relativity, because, technically, you are not moving through space faster than light. You are moving the very fabric of space itself. Sounds wonderful and full of hope, doesn't it? But the problem is, just like wormholes, Alcubierre's warp drive requires a massive amount of exotic matter with an incredibly high negative energy density. The amount of energy involved here is an unimaginably colossal figure. Initial estimates suggested you would need more energy than is contained within the entire mass of the observable universe. Although later research has managed to reduce the energy requirement, it still far exceeds anything humanity could possibly create. And that's just the beginning of the troubles. Creating and maintaining a warp bubble requires an absolutely precise level of control over space-time itself. You would need to generate extremely strong and highly focused gravitational fields, something we currently have absolutely no idea how to do. Furthermore, that bubble must move without harming the fragile ship inside it. There have been deep concerns that anything inside the bubble would be unable to communicate with the outside world, making it impossible to steer or control the ship while in transit. And finally, when you turn off the warp drive, all the energy accumulated at the front of the bubble could be catastrophically released, potentially wiping out and completely destroying your destination in a terrifying blast of radiation. These are truly profound problems, not just mere engineering or mechanical challenges. We're talking about areas of physics that humanity doesn't fully understand, phenomena we've never observed firsthand, and technologies that might be fundamentally impossible. The warp drive, or wormholes, while theoretically interesting, do not, in reality, offer any practical solutions to our problem of interstellar travel. So, we've reviewed all the options together. Chemical rockets are too slow for the scale of the universe. Nuclear fission can only get us to a few % of the speed of light. Nuclear fusion, if we ever get it to work, might reach 10 or 20%. Antimatter, even if we could successfully produce and store it, might get us to 50 or 90% of light speed. but it carries enormous technical challenges. Generation ships demand immense resources and technology, accompanied by overwhelming social and biological risks. Cryosleep doesn't really work yet. Robotic probes, while the best option today, are limited to exploration and cannot help humans settle, and wormholes and warp drives remain purely speculative and are likely impossible. Do you notice a common pattern here? Every single potential solution faces incredibly solid, fundamental barriers. We're not just talking about problems that can be solved with better materials or faster computers. We're talking about ironclad limits imposed by the very laws of physics, by the finite amount of energy available in the universe, and by the very nature of space and time. Now, let's consider another aspect of the problem: the destination. Suppose, by some miracle, we could overcome all these horrific obstacles. We've built a great ship, accelerated it to a significant fraction of the speed of light, and finally reached the Proxima Centauri system after many long decades of travel. What would we find there? The star Proxima Centauri is a red dwarf, a type of star notorious for its extremely violent surface activity. It frequently unleashes powerful flares, horrific blasts of radiation that could wipe out and sterilize any nearby planets. The planet Proxima Centauri b, an exoplanet orbiting within this star's habitable zone, is much closer to its host star than Earth is to the Sunday. This proximity means the planet has likely become tidally locked. This means it always presents the same face to its star, just as the Moon always shows the same face to us on Earth. As a result, one side of the planet would be perpetually scorched by blistering heat, while the other side would be forever plunged into darkness and frigid ice. There might be a narrow strip between these two extreme regions where conditions could be tolerable, but that remains very uncertain and unclear. We also have absolutely no idea if Proxima Centauri b has an atmosphere. The intense radiation from its star's flares may have stripped its atmosphere away long ago. Without an atmosphere, the planet would be uninhabitable, at least on the surface. No air to breathe, no atmospheric pressure, and extremely harsh temperatures. Even if it has an atmosphere, it could be filled with toxic substances like carbon dioxide, methane, or other gases that human lungs cannot breathe. We would need to study this planet in extreme detail before even thinking about sending people to settle there. But doing so from Earth with our current telescopes is still very limited. The best instruments available can only confirm the planet's existence and give a rough estimate of its size and orbit. To determine its atmosphere, surface conditions, whether it has water, or any signs of life, we absolutely need close approach missions with probes, and as we've already seen, those missions would take decades to arrive and another decade for their data to return. And remember, Proxima Centauri is just the closest star to us. Most other stars in the galaxy are much, much farther away. To find a truly habitable planet, a place with a breathable atmosphere, liquid water, a temperate climate, and stable geology, we would likely have to look tens or hundreds of light years away. The number of stars within a 10 light-year radius of the Sun is only a few dozen. Many of them are red dwarfs, like Proxima Centauri. Others are in binary or multiple star systems, where stable planetary orbits are difficult to maintain. The search for a planet truly like our beloved Earth, a place where humans could live without extensive modifications or living in sealed habitats, might require us to search through hundreds of different star systems. The distances and timescales here are truly beyond anyone's imagination. After all those difficulties, the final problem comes down to motivation. Why do we yearn to travel to such distant stars? A few reasons are often given: pure scientific curiosity, an intense desire to explore, the search for extraterrestrial life, or the dream of expanding human civilization beyond the boundaries of Earth. There are also more practical arguments. Our Earth is currently facing many existential threats. from climate change, nuclear war, global pandemics, to cosmic disasters like asteroid impacts or supervolcano eruptions. Establishing colonies on other worlds could serve as a backup insurance policy for the future of humanity. If some terrible catastrophe were to befall Earth, humanity could still survive somewhere else in the universe. This is the famous "don't put all your eggs in one basket" argument. In principle, this sounds very reasonable, but establishing self-sufficient colonies in other star systems requires a level of resource commitment and technological sophistication that is currently far beyond our capabilities. Let's slow down for a moment to consider what we would actually need to make Mars, our closest and most similar neighbor, habitable. Mars lacks a protective magnetic field, which means dangerous cosmic radiation constantly bombards its surface. The planet has an extremely thin atmosphere, composed mainly of carbon dioxide, with a surface pressure that is not even 1% of our beloved Earth's. There, you won't find a single drop of liquid water on its arid surface. At night, the temperature can drop to a horrific negative 125 degrees Celsius. Even the soil underfoot contains perchlorate salts that are extremely toxic to the human body. To survive on Mars, you would be forced to live in completely sealed habitats with complex life support systems, sturdy radiation shields, and you'd have to grow your food indoors. Essentially, you are trying to build and maintain an artificial ecosystem that mimics Earth inside heavily protected structures. As difficult as that is, it's still within our grasp. Because Mars is so close to us, we can still send more supplies, machinery, and support equipment from Earth if something goes wrong. The travel time is only a few months, not several decades. Communication is only delayed by a few minutes, not years. There is always an invisible lifeline between the colony and home. Now, imagine trying to do the same thing on a planet that is light years away from us. There would be no resupply from behind and no hope of rescue. The colony must be completely self-sufficient from the very first moment they set foot there. This means you're not just transporting people, but also all the necessary equipment, tools, materials, seeds, and even animals. This enormous transport mass is far beyond the capability of any propulsion system we have ever discussed. And all of this is based on a risky assumption that you've found a truly worthy planet, a place that won't kill you with a toxic atmosphere or threatening native organisms. There's a very sharp argument that if we have the technological capability to undertake an interstellar journey and establish a colony on a hostile alien world, then we certainly have enough technology to make Earth habitable again. No matter what happens, living underground or in sealed domes on our own home planet is still infinitely simpler and safer than crossing light years just to live huddled in similar domes on a strange world. The colonization of other star systems is not actually a practical solution to the existential threats humanity faces, such as climate change or nuclear war. This so-called backup insurance policy for humankind essentially collapses when examined from a practical and economic perspective. From a scientific viewpoint, sending humans is also far less efficient than sending machines. For every dollar spent to protect a fragile human life in space, you could send 100 sophisticated and much more durable robotic probes. But let's step into a more philosophical realm. Suppose we overcame all physical barriers to build ships that travel at relativistic speeds. How would this affect our very identity as humans? At speeds near the speed of light, the phenomenon of time dilation would cause settlers to age much more slowly than those who remained on Earth. If you send a group of people to a planet 50 light-years away at 90% the speed of light, they might arrive after about 55 years, according to Earth's clocks. But for them, the journey might have only taken about 20 or 25 years. When they land on their new world, more than half a century has passed back home on Earth. All their loved ones are likely gone, and society has changed to an unrecognizable degree. Those settlers are no longer part of the old civilization. They become a separate branch, evolving independently under the effects of new gravity, a new atmosphere, and different kinds of light. After thousands of generations, they might no longer be recognizable as the same species as us. Interstellar colonization is therefore not just an expansion of humanity, but the beginning of a completely alien evolutionary line, permanently severed from its origin. This difficulty may also be the solution to the Fermi paradox, the question of why we haven't seen any trace of intelligent alien civilizations. Perhaps every civilization in the universe is confined to its home star system, isolated in its own small bubble of space, because the distances between the stars are just too vast and insurmountable. The universe might be full of isolated islands of civilization, unable to communicate or interact with each other. Or perhaps civilizations collapse due to internal crises before they can achieve interstellar travel. It's also possible that more advanced civilizations have realized that expanding into physical space is not worthwhile. They might choose to focus inward, building magnificent virtual worlds or transitioning their consciousness into a more durable, non-biological form. Whatever the reason, the harsh reality of physics makes each of us a permanent prisoner on our own planet, separated by nearly impassable oceans of vacuum. Now, let's gently return to our beloved Earth, our tiny blue planet. It is still diligently orbiting a gentle and ordinary star, resting quietly in an unremarkable galaxy in the middle of the void. From our humble perspective, this universe appears almost infinitely vast. There are about 200 trillion stars in the observable universe, and each of those stars holds the potential to shelter its own planets. The distances between these stars are so great that even light, the fastest entity in the entire universe, takes years, centuries, or even millennia just to travel from one point to another. And yet, here we are, on the only world we know for sure, quietly looking out into deep space and wondering if one day humans will be able to reach those distant worlds. The answer, based on everything we have known and understood up to this point, is probably no. At least, not in the near future, not with the kinds of technology we can realistically imagine, and not with the physics we currently understand. The barriers that separate us are not merely technical or mechanical, they are fundamental barriers, etched into the very fabric of space-time. The speed of light is an absolute limit. You can never go faster than that, no matter how much energy you possess. And even at that speed, the distances in the universe are beyond human comprehension. The energy required to accelerate a spacecraft to relativistic speeds far exceeds what our civilization can produce. Perhaps it even exceeds the capabilities of any civilization, unless they can access the immense resources on the scale of an entire star or galaxy. The dangers lurking in interstellar space, from deadly radiation streams and cosmic dust to the need for protective shields and sophisticated life support systems, all create layers of complexity that we may never be able to overcome. And all of this is just assuming you find a truly worthy destination, a planet where humans can live, which in itself is a very big expectation. I am not saying that we should give up trying, nor am I advising you to abandon the dream of exploring the vast cosmos. But it is important that we are realistic about what is possible. The great exploration of the stars, the idea of humanity spreading throughout the galaxy, colonizing thousands of alien worlds and meeting extraterrestrial civilizations. All of those beautiful things will probably remain forever in the pages of science fiction. The reality is that we are confined to this tiny corner of the universe. This confinement is not due to a lack of ambition or intellect, but because the immutable laws of physics have ordained it so. But consider this. Perhaps that is not a bad thing. Perhaps this is a lesson for us to learn, to cherish the only home we have. Let's protect it, care for it, and ensure that Earth will continue to be a place that can shelter future generations. Perhaps the most valuable lesson of the universe is not to teach us how to conquer it, but for us to understand our humble place within it. We are just a young species on an ancient planet, orbiting an ordinary star in a galaxy filled with hundreds of billions of other stars. We are small, fragile, and will likely face solitude for a very, very long time. If there truly are other civilizations out there, they are probably so far away that we could never communicate, let alone visit each other. And that's actually okay. The universe owes us nothing, and it was not created solely to serve humanity. We simply exist within it, like a brief flicker in the grand timeline of the cosmos, trying to find meaning in our own existence. So, in the end, why haven't humans been able to travel beyond the solar system? The answer is that the universe is so vast, our minds cannot fully comprehend it, because the distances between the stars are so immense that even light takes years just to cross them. Because the energy required to propel a ship at a significant velocity exceeds humanity's production capacity. Because the dangers from radiation, cosmic dust, and the cold void are relentlessly harsh to all forms of life. Because we still haven't figured out how to sustain human life on journeys that last for decades or centuries. Because building generation ships or developing deep cryosleep technology is still far beyond the reach of current and even future technology. Because potential destinations remain a risky unknown. And finally, because the laws of physics, from special relativity and thermodynamics to the law of conservation of energy, all conspire to make interstellar travel incredibly arduous, if not outright impossible. It's not because we aren't intelligent enough, but because the universe is structured in a way that keeps everything at a distance. And perhaps that is the ultimate lesson for us. We live in a universe designed for isolation. Stars are separated by light years of vacuum. Galaxies are separated by millions of light years. Even if we could travel at the speed of light, which we can't, the vast majority of the universe would still be forever inaccessible, as it's being pushed away beyond our cosmic horizon by the accelerating expansion of space itself. We are confined to this small corner, not by choice, but by a grand design. And perhaps that is something we must learn to accept. The universe is vast, beautiful, and full of mysteries, but most of it is beyond our reach. We can study it, we can observe it, we can send robotic probes if we're lucky, but to set foot there ourselves, to walk on the shores of a distant world, or gaze upon alien suns that may forever remain just a beautiful dream. Tonight, we have journeyed together through the invisible barriers that separate us from the stars. We have seen the unimaginable distances, the insurmountable energy requirements, and the cruel limits of physics. This is not a happy story in the conventional sense. It doesn't end with humanity conquering the galaxy. It ends with the profound realization that we are, and perhaps always will be, confined to this small, blue planet. But within that realization lies a strange beauty. It reminds us of how precious this Earth is. This is the only home we have. Instead of forever dreaming of an escape to distant stars, perhaps we should devote our energy to making this world the best place it can possibly be. Thank you for taking the time to join me on this journey through the limits of possibility. If you found this exploration deeply valuable, a like or a subscription would mean a great deal, helping to motivate the channel to continue creating meaningful content like this. I wish you a very good and peaceful night's sleep, secure in the knowledge of your place in this vast universe, no matter how small that place may be.